Welcome to part 2 of roots and coefficients in the topic of polynomials. We now move on to cubics. The general form of a cubic equation is ax cubed plus bx squared plus cx plus d equals 0. The a will always be the coefficient of the highest power, and the b, c, and d will be the coefficients of the subsequent powers. When we divide by a to get a monic cubic, we get all the other coefficients as fractions over a. If the polynomial is already monic, which means that a has a value of 1, we won't need to write them as fractions over 1, we just leave them as the integers. This time though, we're going to need to have another term for the third root that comes with a cubic. In this case, it's called gamma. It sort of looks like a y and is the third letter of the Greek alphabet. So we now let our roots be alpha, beta, and gamma. If we expand the factorized equation with those roots, we will get x cubed minus alpha plus beta plus gamma x squared plus alpha beta plus alpha gamma plus beta gamma x minus alpha beta gamma, which will equal 0. This is a bit of a tongue twister, but if we look at the roots, we will notice that alpha plus beta plus gamma is the sum of the roots. Alpha beta plus alpha gamma plus beta gamma is the sum of the products of each pair. And finally, the alpha beta gamma is the product of the roots. And this is how we find our new equations. We can write those as alpha plus beta plus gamma, which is going to be minus b on a. Alpha beta plus alpha gamma plus beta gamma is c on a. And alpha beta gamma is going to be minus d on a. Notice how the negative sign alternates between the different roots. This will become important in later examples. Let's look at example 15. We are to show that alpha squared plus beta squared plus gamma squared equals the sum of the roots all squared minus 2 lots of the sum of the product of the pairs of roots. This example is going to give us an identity that we can use in our future working out if we come across the sum of the squares of the roots. From any given equation, we can use the coefficients to find the value of the sum of the roots and the sum of the product of the pairs of each root. We will write the sum of the squares of the roots in these terms. This question, however, is asking us to show. This means we need to take one of the sides and show through the use of algebra it will equal the other side of the equation. We start with the right hand side. This equals the sum of the roots all squared minus 2 lots of the sum of the product of the pairs of roots. By expanding the first bracket, I get a fairly long string of algebraic terms. You should try and do this for yourself and see if you can't get the same answer that I do. Notice that within the string of terms is an alpha squared, beta squared, and gamma squared, as well as identical pairs of alpha betas, alpha gammas, and beta gammas. On the end of that, I don't forget my second part of the right hand side, which is minus 2 outside of the sum of the products of the roots. I could have expanded that out as well, but you'll see why I don't in just a moment. Rearranging the first part, I get alpha squared plus beta squared plus gamma squared plus 2 lots of the sum of the product of the roots. To the end of this, I subtract 2 lots of the sum of the product of the roots. These two will now cancel each other out, leaving me with just alpha squared plus beta squared plus gamma squared, which is the left-hand side. And we've shown what we needed to show. Now each time you get the sum of the squares of the roots, you can write them in terms of things that you know from the equation. This will make your life a lot easier. Let's try example 16. Here we are given the polynomial, told that the roots are alpha, beta, and gamma, and then asked to find the value of a few different expressions. Take the time now to pause the video and try to solve the first few for yourself. Go as far as you can without help, and then continue with the video for solutions. Okay. For a, we are asked to find the value of the sum of the roots. The sum of the roots is given by minus b on a, which is just going to be the coefficient of the x squared term. In this case, it's minus 2. Don't forget that it has to be negative for the coefficient of x squared. This is something that many students make mistakes on. For b, we are asked to find the sum of the product of the pairs of roots. This sum is equal to c on a, which is the coefficient of the x term, which in this case is just 3. There's no need to change the sign in this case, so it just stays as positive 3. C asks us to find the product of the roots. The product of the roots is equal to minus d on a, which in this case is negative 4, which is just the constant. Again, we have to change the sign of this answer to a negative when finding it. Question D is written as a product of 3 binomials, none of which are in the forms of the questions A, B, and C. So we're going to have to do a little work on it so we can write them in terms that we know. I start by expanding the brackets. Try this for yourself and group together the like terms. you should get an expression which involves all three questions from A, B, and C with a -1 on the end. Equating each of these answers, we get a value of -10. If the question isn't written in any of the three familiar forms, try manipulating the expression with algebra until it looks the way you want. Isn't maths great that it can just do that for you? Moving on to E. It looks tricky and is definitely not written in the form that we like. However, we can add these three fractions together to get another fraction written in terms of the values that we know. In this case, the final answer is going to be -3 on 4. The numerator in our expression comes from question B, and the denominator in our expression comes from question 4. Note that this is -3 on 4 and not just 3 on 4. Question F asks us to find alpha squared plus beta squared plus gamma squared. We know that we can rewrite this as alpha plus beta plus gamma all squared minus 2 lots of the sum of the product of the pairs of roots. In this case, when substituting in, we get -2 squared take away 2 times 3. The answer is -2. Finally, G. This looks similar to question E and is solved in a similar manner. By getting a common denominator of alpha, beta, gamma, we can write the numerator in a form that we like. We then substitute in the values we got from questions A and C to end up with a value of 1/2. We will now practice an example that uses these ideas to solve a polynomial all in one go. Example 17 asks us to solve this polynomial given that 2 of the roots are equal. We could probably use the factor theorem to solve this question, but let's see if we can't use our algebraic skills to get the answer instead. If 2 of the roots are the same, then our 3 roots will be alpha, alpha, and beta. It doesn't matter if you have 2 alphas and a beta or 2 betas and an alpha, you're still going to get the same answer. The first thing you should do when solving something like this is to write down what you know from the coefficients of the polynomial. We know the sum of the roots, which can be simplified to 2 alpha plus beta equals 7 on 2, which is -b on a. We also know the sum of the product of the roots. This can be written as alpha squared plus 2 alpha beta, which from our coefficients is -6. We also know the product of the roots, alpha times beta, which can be simplified to alpha squared times beta. This is going to be -45 on 2, which is -d on a. These are our 3 equations, and we are now going to rearrange some of them to get the values for either alpha or beta. I can rearrange question 1 in order to get beta equals 7 on 2 minus 2 alpha. This now gives us beta in terms of alpha. We can now substitute this into our second equation to get alpha squared plus 2 alpha times 7 on 2 minus 2 alpha, which will equal -6. We can rearrange this to alpha squared plus 7 alpha minus 4 alpha squared equals -6, which we finally rearrange to get a quadratic. We can then factorize this to 3 alpha plus 2 outside of alpha minus 3, which equals 0. This is going to give us 2 solutions for alpha. Alpha is either going to be 3 or -2 on 3. What we're going to do is we're going to substitute those values of alpha back into our first equation, and we're going to get values for beta as well. In this case, beta is -5 on 2 or possibly 29 on 6, depending on what we substitute in. In order to work out which one is which, we're now going to substitute those values, those pairs of values, into our third equation. So we're going to substitute alpha equals 3 and beta equals -5 on 2 into our third equation in order to see if it works out. So the left-hand side of our third equation is going to be 3 squared times -5 on 2, which gives us an answer of -45 on 2, which is exactly the same as our answer for 3, which is the right-hand side. If we then substitute in our other value, which is -2 on 3 and 29 over 6, we get a final answer of -58 on 7, which is not our right-hand side. This means that -2 on 3 and 29 over 6 are not our answers for alpha and beta. We can now say that the roots of our equation are going to be 3, 3, and -5 on 2. In our final example, we will be challenged in our algebraic skills as the polynomial is not written with numbers for coefficients, but pronumerals themselves. We are told the roots of x cubed plus px squared plus qx plus r are consecutive terms of an arithmetic series, and we are asked to find an equation which will link p, q, and r together. Now, before you freak out about what an arithmetic series is, it's just a set of numbers that have a common difference. Like 1, 2, and 3 is an arithmetic series because it has a common difference of 1. 2, 5, and 8 is also an arithmetic series because it has a common difference of 3. You may not have heard this term before, but we are going to write out our three roots as alpha minus beta, alpha, and alpha plus beta. These are three roots with a common difference of beta. Now we are going to write out our three forms in the terms of our roots. So the sum of our roots equals minus p, this is the negative coefficient of x squared. So 3 alpha is going to give us minus p, which is our first equation. The sum of the products of the pairs of our roots will equal q. This looks horrible, but when I expand it out and simplify it, I get 3 alpha squared minus beta squared, which equals q, which is our second equation. Our third equation comes from the product of the roots. This is alpha times alpha minus beta times alpha plus beta, which is going to give us minus r. This will be our third equation when we simplify it to alpha times alpha squared minus beta squared equals minus r. Again, this is a difference of 2 squares. From 1, we get alpha equaling minus p on 3. We can now sub in this into 2 to get an expression in terms of p, q, and beta. This simplifies to beta squared equaling p squared on 3 minus q. Now we're going to sub this into 3. Alpha outside of alpha squared minus beta squared equals minus r. That's our third equation. Now that looks horrible, but that is a substitution of alpha is minus p on 3 and beta squared being p squared on 3 minus q. And the reason why we've done this is because we've gotten rid of all the alphas and all the betas, and our equation is now in terms of p, q, and r. All we have to do now is simplify our equation. We do this by expanding the bracket that's inside the internal bracket, and we multiply both sides by 3 in order to get rid of the 3 that is on the bottom of the p here, which leaves us with just a p outside our bracket. By expanding this out again, we get p outside of p squared minus 3p squared plus 9q equals 27r, and we do this by multiplying everything throughout by 9. And then finally we simplify with p outside of 9q minus 2p squared equals 27r. And we've written our equation linking p, q, and r together. We end the video not with any more examples, but what the roots of a quartic equation will look like. With a quartic equation comes another root, and another root means another Greek letter. This is the general form of a quartic. By dividing by a, we get the monic quartic polynomial shown here. We let the roots be alpha, beta, gamma, and now delta. Although I have seen people who find it less confusing just to use A, B, C, and D. It's up to your preference, but be wary of questions that involve the use of English letters already in the question. If we write the quartic in its factored form with the roots, we can expand it to get, this is a horrible expression, full of alphas, betas, gammas, and deltas. Now, before your head explodes, let's take a little bit of a look at what the roots and the coefficients of the x's are. We start with an x to the power of 4 because it's a quartic. But notice that the coefficient of the x cubed is the negative of the sum of the roots, which is the same for all the cubic and it's the same for the quadratic. The coefficient of the x squared is just the sum of the product of the pairs of the roots, which is just the same as the cubic. And the coefficient of the x is the sum of the products of the triples of the roots. And finally, the constant is the product of the roots. There is a pattern to the coefficients and the roots of the equations in a polynomial. This topic will really stretch your algebraic mind and see how good you are at manipulation. The key is to not give up on tricky questions, as you may find questions easier as you go through your exercises. Another tip is, once you understand a particularly hard question and have finally gotten the solution, see if you can't write it from scratch on a blank piece of paper to understand each step. This final screen gives a handy list of the identities that may be useful in your solutions to your problems. Write them down and have them next to you as you're working through your solutions. Good luck.